Welcome everyone to Interactive Computing with Jupyter. We're focusing on Piz Daint here, so we're not going to teach you how to use Jupyter or even Python. We're going to teach you specifically how to use it for Piz Daint. We're going to focus on three main topics: Python, obviously, which is what people generally use with Jupyter, and also ParaView, and in particular, how to use ParaView with the JupyterLab that we have on Piz Daint. And then we're going to focus on Julia as well. So perhaps a little known fact is that Jupyter kind of stands for Julia, Python, and R. And although the vast majority of people use Python with Jupyter, you could also use Julia, and Julia is becoming kind of an up-and-coming language that might be useful for HPC and other applications in data science. So we'd like to introduce you a little bit to Julia. My name's Tim, and I'm here with my colleagues Jean and Harman. So Jean will be doing the visualization stuff with ParaView, and Harman will be doing the Julia section. Just quickly, what we're going to run through today, we're going to talk about Jupyter, Jupyter Notebook, JupyterLab, and JupyterHub, and differences between those three things. So we're going to talk about Jupyter, and then we'll grab a break at about 10:45 for 15 minutes, grab a coffee, or whatever your beverage of choice is. I guess most of you are joining from Europe, so it'll be breakfast time. Then after 11 o'clock, Jean will give the first half of the ParaView and Jupyter section. We'll grab some lunch for an hour between 12 and 1 o'clock Central European summertime. And then we'll have another hour of ParaView, a small break, and then we'll jump into some programming in Julia, where Harman will talk about GPU programming and Julia in general. So let's get started. Jupyter. Most of you probably have used Jupyter, most likely on your laptops to start with, and perhaps you've used it on Piz Daint. Let me see if I can grab the chat. And perhaps you can write in the chat if you've used JupyterHub on Piz Daint or not. Just stick something like a yes or a no, so that we get an idea of. So a few yeses, predominantly no, I would say. So maybe 20% yes, 80% no. Okay. So notebook. When people say Jupyter Notebook, they mean two different things usually. It's the web app that you are connecting to in your browser, and this enables you to run code, usually in Python, but can be in other languages. And it gives you a bunch of different functionality, ranging from being able to write some descriptive text to put some LaTeX equations. And you can have live code, you can have output visualizations, you can do cool things like widgets, and you basically can create a computational narrative. And I suppose it's kind of akin to people doing bench science, maybe physicists, chemists, biologists, who would have a lab notebook. And so you would write down some equations, you would write down some methods, maybe draw a figure of some results, and you would keep this in your lab. So the Jupyter Notebook's kind of similar to that, but in a computational style. You can export your notebooks to PDF, HTML, LaTeX, and whatnot. And then the Jupyter Notebook is also the file itself, which is this notebook file, and it has the extension IPyNB. It's a JSON formatted file format, and so we also call that the Jupyter Notebook. So it's both the web server and the actual document itself. The document you connect to a kernel. So Jupyter, they talk about a kernel. What they really mean is just simply what's running in the back end, which is executing your code. And usually that's an IPython kernel. But as I say, it can be other things. It can be Julia, it could even be C++ or Fortran. JupyterLab is simply next generation of Jupyter Notebook. So Jupyter Notebook is on the top here in this figure, and JupyterLab on the bottom. You can consider Jupyter Notebook as a sort of a very linear up and down sort of old style HTML page that you can just scroll up and scroll down. You can see some visualizations and whatnot, but you can't really have too much flexibility in how you arrange your workspace. So imagine you execute some code up here and it produces a figure further down your notebook. You need to continuously scroll up and down, and it's kind of a nuisance. Whereas JupyterLab on the bottom, you can see it's a richer environment. You've got different windows that you can arrange in different ways, and you can even have different parts of your notebook in different places. So here, this is, for example, a visualization, an output cell, which could be anywhere on this notebook, and I've just chosen to arrange it over this side so that it's always here, no matter how I scroll up and down my notebook. And you can also put some Python file, you can have a terminal, you can do all sorts of stuff. The important things to note for you is if you haven't used JupyterLab before, it's the same notebook format. So you can just use your same Jupyter notebook and it will work in JupyterLab without any problems. At CSCS, we use JupyterLab as the default interface. And we have, I think, since JupyterLab was released a couple of years ago, you can still use classical notebook, Jupyter Notebook, or what they call classic notebook. And you can do that by just changing the URL from /lab to /tree. And the other option is you can go through the menus and go help, launch classic notebook. And that will move you from JupyterLab back to Jupyter Notebook if you're more comfortable with that older style interface. However, I kind of recommend try out JupyterLab because eventually the Jupyter Notebook will be discarded in favor of Lab. So even though I know some people still like using notebooks, it's a bit simpler and a bit more easy to manage. Lab will be, Lab is the future. So try out Lab. Finally, JupyterHub. So what is the difference between JupyterHub and Jupyter? So basically, JupyterHub is just a multi-user environment. So all it does, as far as you're concerned, you don't need to know too much about it because we provide the JupyterHub for you at CSCS. And all that is really doing is spawning a Jupyter notebook for you. And it deals with things like authentication. So it prevents, so it makes sure that your browser window connects to your notebook and doesn't connect to another user on Piz Daint, for example. And JupyterHub is basically a collection of spawners. We use a Slurm spawner, which is one of the options. There can be other spawners like SSH or Kubernetes if you're using a cloud native environment. We use Slurm on Piz Daint, so we use Slurm spawner. And basically you just go to a website and you click on launch notebook. And then it deals with all the proxying of your network traffic to ensure that the notebook ends up at your browser and you're running on Piz Daint. How do you get there? For those who have not used it so far, it seems like there's quite a lot they haven't used. So it's available at https://jupyter.css.ch. And it's available to anyone with a compute allocation on Piz Daint. So if you have an allocation on the multi-core, then you can use Jupyter notebooks on the multi-core part of Piz Daint. Likewise, if you have an allocation on the GPU part, then you can use Jupyter on the GPU nodes. Simple as that. Unlike some other Jupyter hubs that you might have used at other centers, we don't use shared nodes. Basically, you launch your notebook and you have dedicated node for that notebook. And it can be one or more nodes depending on what you choose at the spawner page. So you will get the full capability of that node and you will pay for it from your compute allocation. But the advantage is that you'll have all of the memory, you won't be sharing with any other users, and you'll have access to the GPU, obviously, if you have a GPU allocation. How do we ensure that you can get a notebook in a reasonable amount of time? We have special reservations in Slurm, and these interactive reservations, they grow and shrink according to demand. So if you come along and grab a notebook, and that grabs one node from Piz Daint, then the Slurm reservation will automatically insert another node into that reservation. So the next person that's coming along will be able to start their notebook in a short period of time. And in most cases, you should have to wait less than around 5 minutes for the allocation. So there is a little bit of stuff that Slurm needs to do. We have a Slurm scheduler that has various cycles every few minutes or so. So you might need to wait a minute or two, but you should always have an allocation within a few minutes. And indeed, if it takes longer than 7 minutes and it's still queuing, it will actually cancel the submission. And in that case, it would be great if you wrote to us, wrote a ticket through the support.cscs.ch and tell us that, you know, I tried to launch a notebook and it didn't launch in 7 minutes. It threw me out, because we need to know those things so that we can fix them. How many users do we have on JupyterHub? So you can see here, this is monthly users for the last 2 years. So every bar here refers to 1 month. You can see last month we actually had the most users we've had, more than 70. And it says on the whole, it's generally growing over time. So more and more people are interested in using Jupyter. Perhaps they have some large data set on Piz Daint Scratch file system, and they need to do some Jupyter and some analysis using Python of that data. Then it's an ideal use case. Jump onto Jupyter Notebook, run your analysis, and then you don't need to move all of that data from Piz Daint to your local machine or something like that. So I see that there's a question in the chat already. Is there a time limit on how long I can have the notebook open? Yes, so the maximum time for the notebook is the same as the maximum time that we have for standard jobs in Slurm on Piz Daint, which is 24 hours. And we'll see that when we come to the spawn page in a moment. There are some challenges with interactive computing on HPC. So it's not all roses. You have some various elements that can slow things down. And when we generally talk about interactivity, you kind of expect everything to be immediate. If you've used Jupyter on your laptop, you install Jupyter, you run, and everything is pretty much instant. It's all great and wonderful. And then when you move to a high performance computing system, you kind of expect it's going to be faster and better and everything, but not always. So there are a variety of things that are shared across Piz Daint, and this can lead to slowdowns. So for example, the file systems. We have a couple of large parallel file systems, the Scratch, which is a Lustre-based file system, and Home, which is GPFS or Spectrum Scale from IBM. And these are shared by everyone. And for this reason, you know, parallel file systems is actually a difficult problem, and it can lead to some lagging or slowness if there are problems on those file systems. So if you imagine some other user is thrashing one of the file systems, maybe doing a lot of metadata operations, for example, then it can actually impact the response on your notebook. And so you'll be sitting there, you know, going through your shift enter on your cells, and suddenly something stops working or it's sluggish, and you think, oh, what's going on? I don't know. Suddenly it's gone slow. It could just be something to do with the file systems lagging, and you just need to wait 1 or 2 minutes for the response to return. Likewise, network connectivity, the internet. So this thing is tricky to debug. It could be a problem with your own internet connection. It could be something between Piz Daint and your browser. It could be something within CSS center, it could be coming back to your browser. There's many, many different places where there can be a point of failure or slowness in the network. So again, it's tricky to debug, but just usually leave it a minute and see if it returns. If you have longer delays, then send us a ticket through the support. Slurm is another thing. So if someone is thrashing the Slurm control daemon, then perhaps Jupyter thinks that your notebook has died when it actually hasn't. So the way that JupyterHub works is that it periodically does kind of like an SQ back to Piz Daint, and it sees if your notebook is still running. And if the notebook has stopped, then it tidies everything up. So if it doesn't receive any response from Slurm for many minutes, it might think that your notebook has actually died, and then it cleans everything up and deletes your notebook. So this used to happen a little bit in the past, and we have put some new fixes in recently in the last couple of months. So this particular problem should not happen any longer, but if it does, send us a ticket. Another thing that can happen, which is another thing which is kind of not easy to debug, is if the system engineers are doing something on the system and like a warm swap. So for Piz Daint, it's a Cray XC system, and the beauty of it is that you can actually swap blades in and out without shutting the whole system down. So imagine that you have some nodes that went down on Piz Daint and the engineers need to replace them. They can actually swap out an entire blade and swap it back with another one, and the system will keep going for everyone running jobs on the system. Now, the complicating factor is that all of the networking traffic needs to be rerouted because it can obviously no longer go through that blade. And this rerouting takes some time for the network to adjust. So all of the MPI activity, all of the IO and everything which is buzzing around the system needs to be rerouted. Routing tables need to be adjusted. And so you can see some kind of delay sometimes. So again, this is a delay which could affect you, but it might not affect you. And these are not operations that happen all the time, every few weeks perhaps. But you might see suddenly that there's a lack of response on your notebook for a couple of minutes, and you've just got to wait again. And there can be all sorts of bunch of other things that can go wrong as well, but they're usually just temporal problems. So just have some patience, and things usually get back to normal. To try to debug, there's a bunch of things that you can do. First of all, we have an announcement service on the JupyterHub main page. So you can check for any announcements of known problems or known upcoming maintenances directly from the spawner page. Next thing to do is obviously check your own internet connectivity, just check that there's no problem at your end. Check for old JupyterHub sessions in other browser tabs or other machines. So imagine you have multiple laptops, or you have multiple browsers with multiple tabs. If you relaunch a new Jupyter session, it could be that your token is connected with the old one, which is now stale. And in this case, Jupyter will have a problem connecting to your kernel. So if kernels are really slow to start, or you have trouble reconnecting to old kernels, then please check that you don't have Jupyter open in another tab in your browser. This is not actually supported by Jupyter to have the same notebooks in multiple tabs. We have a log file which is written to your Scratch directory. When you launch your notebook, you can see the location of that file because it's printed to the screen just before your job starts. But it just sits directly in your Scratch directory, so it'll be the most recent file in your Scratch. If problems persist, please use our new ticketing system. So we've just migrated recently from email to a Jira service desk support. So you can go to support.cscs.ch and submit your ticket. And please include as much information as you possibly can about the problem, because it's even hard to debug from our side, Jupyter, or interactive computing in general. So give us the precise time periods that you are using the notebook, the job ID, what was working and what was not working. So if you just say, I couldn't launch my notebook, or my notebook was not working, it's very difficult for us to debug. But if you say, I was already in my notebook and suddenly the cells stopped executing or something like that, then it helps us a lot. What does the JupyterHub look like on Piz Daint? So we have a virtual machine, which is this jupyter.css.ch, and that's sitting outside of Piz Daint. And that's where the JupyterHub web server is actually running. So when you connect to jupyter.css.ch, you're jumping onto this JupyterHub web server, and that deals with the authentication. So you just use your normal CSS username and password, uses OAuth2 based on Keycloak. And you click spawn, and that basically launches a Slurm job, as I say, onto a compute node of Piz Daint. So this yellow is a compute node on Daint. You have access to the file systems, so Scratch, Home, Project, and whatnot, because they're all obviously mounted from the compute node. And your notebook server itself is running on that compute node. From there, you can run your kernel on the compute node. And if you use things like PyParallel or Dask, various ways to do distributed or multi-processing using Jupyter, you can do that within the node, and you can also do it across multiple nodes. And we will show you later on how you can achieve that. Okay, so what does the interface look like? You go to jupyter.css.ch and log in, and you'll see something like this. It's pretty straightforward. There's node type. So as I mentioned, if you have an allocation on the GPU, you can use the GPU, otherwise you can use the MC. You can choose the number of nodes. Most people would typically use one node, but you can use multiple node if you can make use of it. Again, then you need to use some kind of distributed computing in Python, such as IPyParallel or MPI for Pi. And then, alluding to the question I was asked before, you can have a duration that you launch your notebook for, and it can be from 1 to 24 hours. It's important to know that you can shut down your notebook as well. So you might want to choose sort of an 8 hours for duration, just because you expect to use it during the working hours. And then if you want to shut down the notebook, you can do that from the file menu inside Jupyter. But here, if you select a duration, it will actually kill your notebook after that amount of time automatically. So it'll basically does an S cancel on your Slurm job after that amount of time. And then you click launch, and it's as simple as that. And generally, that's all you will need to do for your notebook to work. There are some advanced options, and we can quickly go through those. You can choose the queue that you want to use. So as I mentioned, we have this special reservation, which kind of grows and shrinks according to demand. And that you can use that for up to 5 nodes now. So if you want more than 5 nodes, then it will go into a standard queue. If the special queue is not working for some other reason, then you can choose to use the normal queue by selecting from the drop-down menu. Project ID. You might belong to many projects at CSS, so you can specify the specific project ID or account that you want to have the allocation connected to. Advanced reservation. So for example, this course, we have a reservation called tutorial. So in this instance, you will need to write tutorial in this box. And then you can select the JupyterLab version. So we usually have 1 or 2 different versions of JupyterLab available. At the moment, the default is 1.2.16. We do have a JupyterLab 2 available that you can try out, and we'll soon have JupyterLab 3, which is the most recent major version of JupyterLab. And then in the past, we had a couple of options to start with using IPyParallel and using Dask distributed. These things are now a little bit out of date. So we prefer you not to use, in fact, we might remove these from this page in the near future, because we have smarter ways to do this now. So in the past, you could start an IPyParallel cluster with MPI using these options, but now we've replaced this with some magic, Jupyter magic functions that we've implemented here. And so I'll show you how to use that in a second. And likewise for Dask distributed, instead of using this, we now recommend you to use Dask Lab extension dashboard or Dask job queue for distributed computing. And again, we'll touch on this when we get to the hands-on. So then you click spawn and you arrive at the JupyterLab interface. And you'll see that there's a few different kernels available, Julia and Bash and Python. We'll have a look at those in a minute. You've got your main workspace here where you can launch your notebooks, terminals, everything you need. There's a browser. You can see that you're put into your home on Piz Daint by default. And you need to access Scratch and Project. You might need to make some soft links. So ln-s, again, I'll show you that when we do the live hands-on. And as I mentioned, the standard out and standard error is written to a log file. So this is your kind of first port of call if you have any problems on Jupyter. To shut down the notebook server, if you don't want to let it expire after the duration that you specified, then you can go Hub control panel and stop my server. It's important that doing a log out will not actually stop the server. So log out will log your user out, but the server will continue to run. To actually stop the server, you need to go File, Hub control panel, stop my server. Okay, so probably the #1 question that's asked by people is, how do I get the Python packages that I need for my project? Because JupyterLab that we provide on Piz Daint will include some packages. So it includes a version of NumPy, a version of Pandas, a version of Matplotlib, and so on. But typically you have your project when you need specific versions or specific packages. So there is a variety of ways to install Python packages, and some of the ways are better than others, but we will introduce all of them in the hands-on in the live demo. The simplest way is just to type pip install, and you can do that directly from a notebook. And that will make that package available to all of your notebooks because it will install it in .local lib, blah, blah. A better way is to use virtual environments and then to convert those virtual environments into kernels. I'll show you how to do that as well. Another way to get some stuff into your notebook is to do module load commands that you can place in a special file called .jupyterhub.env. And that should sit in your home directory. So basically when Jupyter spawns your notebook, it sources this file, .jupyterhub.env, and anything that you have in there will then be sourced into your environment. So for example, if you want to have TensorFlow available in your notebook, you would have module load TensorFlow in that .jupyterhub.env file, and then as if by magic, you'll be able to use TensorFlow in your notebook. If you prefer to use Conda, you can install Miniconda, and then you can use Conda environments. Again, we'll have a look at how to do this in a second. And final thing that we're looking at is containerization. And this could potentially allow you to spawn your own JupyterLab. So at the moment, basically what you're getting is JupyterLab that we provide, and then you can build Python modules inside that, or you can use your own kernels inside that, but you can't use your own entire JupyterLab executable. And we could solve that with containers. And if anyone is interested, because you have a particular use case, perhaps you have a JupyterLab extension that you want to use, but CSS does not provide that, then that would be a great use case. And so please be in touch with us. I mentioned IPyParallel. So we have a magic available now, which is %IP cluster, and that allows you to start IPyParallel clusters. And to enable that, you have module load IPC magic in this .jupyterhub.env file that I mentioned. And then you do an import IPC magic in your notebook, and then you can start MPI for Pi, and this will allow you to use MPI directly from the notebook. We'll have a look at that again soon. We have a couple of special dashboards, a Dask dashboard and a GPU usage dashboard that comes from the NVIDIA folks. And so you can see the GPU utilization, and you can see utilization of Dask if you're using that. And again, we'll have a look at those extensions in a moment. Here's the GPU dashboard. I don't expect you to be able to read this in detail, but you can see that there's various panes that show compute usage on the GPU, memory usage, and timelines that show the various resources like compute, memory, PCIe, throughput, and these types of things. So you can see as you step through your code how the GPU is being used, and in particular how the memory is being allocated is very interesting to see. So you can see that whenever there's allocations and deallocations, you can have an idea of how the GPU is being used. And significantly, these dashboards are not, so they are running in the background and observing all usage of the GPU or all usage of the CPU, not just usage from the notebook. So there's nothing to stop you from bringing up these dashboards and then running your GPU code from the command line with a / or srun /. You will still be able to see this information. So it doesn't need to be necessarily a Jupyter notebook. It can be any kind of executable. So that's kind of cool. It's a simple way of doing a basic profiling of your code. Okay, so that's the presentation. Now I'm going to share the actual browser, and we can have a look at the way that we use some of these things live. You can follow on with your own account that you've been sent by email, or you can just watch and ask questions as we go. It's entirely up to you. Everything good? You can view? Yeah. So as I mentioned, you go to jupyter.css.ch and you're presented with this screen, and after you've logged in, so you can see that I'm logged in as Robinson, and I can immediately just launch my notebook. So I'll bump the duration up to 2 hours. If we're using the reservation here, we can type tutorial, and then we can simply click launch. And if everything goes to plan, we'll be able to see that the notebook is able to start. So here you can see, as I mentioned, that this tells you what that the log file is going to be available at that $/JupyterHub_slurm spawner. And then the server is ready, starts up, and you're presented with this main workspace. We have a few cool things that you might not have seen on other places. We have a memory monitor at the top. So you can see that the total amount of memory available is of the order of 60 gigabytes. And you can see as memory is allocated, then this is going to be a bar that moves across the screen, so you can get an idea of that. We've got 3 different kernels that are available by default. We've got a Python, obviously, Bash, and a Julia kernel. And then you've got your home directory along here. And you can see that the root directory of the notebook is /users/your username. So basically the $home. Now, it's important to note that you cannot move up a directory tree from this interface. And we know that your Scratch directory and project are mounted as /scratch or /project. So you can't from here move from /users back up and then down to Scratch. So what we need to do is to create a symbolic link to make these directories available. What we can do, we'll show you that in a second. Let's have a look at first of all, there's a bash kernel. I don't know if you want to use bash, and maybe for I in 1 to 5, do something, echo it. You can see that you can use bash, which is kind of cool. So maybe you have some simple scripts and you want to use bash, you can use this kernel. And you can see that the state is retained across different cells. So it's really more or less just like using bash in a terminal. So that's kind of cool. Likewise, we've got a Julia kernel. This will be discussed more by Harman later on. We recently upgraded to 1.6.0. So I think last week it was 1.5. We now have 1.6. You can see the kernel's connected. We can do something in Julia. 1 + 5 is 6. Great. And you can use the package manager. So we're using package, see what's available. If example is available, no. So we can install something with package.add. Harman will talk to you about how to use Julia this afternoon, but just give you a flavor. You can hopefully add packages into your environment, and then you can use it. And then you can, I don't know, write hello world or something. Hopefully print hello everyone. Yeah, so Julia is there for you. As I say, I don't want to steal Harman's thunder, so we'll close that one up. Over here, you can see that the kernel sessions, we shut down the kernels that we still have running. You've got a terminal that you can pull up. And so, as I mentioned, the notebook is running directly on a compute node of Piz Daint. So you can see that here, that it's NID 02381. And so that indicates that you're on a compute node. If you were on a login node or something, it would probably say Daint 101 or Daint 102, something like that. So you can see that it is a compute node. You can do your standard terminal stuff like top. If we have a look at what's running from my account, you can see that there's some Python, which is running JupyterLab. There's a thing called batch spawner single user, and that's effectively the notebook server itself. And Slurm script. Again, we can close. It's important to know that kernels and terminals actually keep running if you close with the X. So we can see that if I close this with X, then I go over to my kernels, you can still see that the terminal is actually running. So I can then reopen it again. If I run top, you'll see that this is indeed the case. If I close this and then I click back on it, it's still running. So if you really want to close the terminal properly, you need to either type exit or you need to force the shutdown of the terminal. There, I'll go exit, and you can see the terminal session's finished. Let's have a look at an example notebook. So what I've done actually is put these notebooks on GitHub, so you can pull them down if you like. What we can do is I will show a command. If you File, New, Notebook, then you should be able to do these directly from a notebook. So we'll go File, New, Notebook. And then the command to pull it down is git clone, and then the name of the repo. What I'll do is I'll put that in the chat for you as well. And so those not so familiar with Jupyter, this bang operator basically tells you I want to run a shell command. And so I'll do git clone, and then, whoops, will work for you. I've already cloned this repo. So you can type bang git clone. Maybe someone in the chat just say that it's working, and you're able to get these notebooks. Yep, great. And we'll open up the first one. Okay, perfect. Sounds like it's working. So people have got the notebook. So go into the notebook, and the first thing that you need to run, as I mentioned before, you don't have access to your Scratch by default. So again, what you can do is you can use this bang operator and do a soft link or symbolic link to $scratch, which will be something like /scratch connection 3000 / username, and we can just call that whatever you want. So I'll just call it Scratch, type that, and then you'll see, as if by magic, the Scratch directory will appear for you in your file browser. Okay, so here it was not there before, but now it's here. And so you can do the same, and then I can click onto that Scratch folder, and then you'll see all of my files in Scratch. Okay. As I mentioned, there's this slurm spawner _ job ID.log file, and that should be your first port of call for any debugging. So again, we can cat that file, or we can at least we can ls it to if I do ls-alt, I'll get the most recent file at the very bottom, and you can see that this is the log file that's today's one, April 26. So then maybe we can tail that. Oops, spelling's a bit off. So yeah, you can see that kernels are starting and those types of things. So this is, yeah, your log file. And you can also just SSH into Piz Daint, have a look at that log file. But we try to do as much in the notebook as we possibly can, of course. As I mentioned, most questions about Jupyter revolve around where is Python finding this package from, or why are some things, some Python modules available and some things are not. So let's, in the next few minutes, try to understand where everything's being found from. Some things are available by default, so you can use IPy widgets. You can see here, this is basically the most simple possible widget. And I can run that. We can w.value, see that it works. Likewise, matplotlib, this is available for you. You can do a simple matplotlib inline and have a chart. But that doesn't tell us exactly where these things are coming from. So first of all, we have the main site packages directory, and pretty much everything is built on top of the Cray Python module. So the equivalent to if you were SSHing into Piz Daint and you do module load cray-python, then this will give you this Python distribution, and it's sitting in OPT Python 3.8.5.0. But obviously this is a centrally installed thing, so you don't have any rights to be able to add packages into there. So the question is, how do I put my packages into where I want? And we'll see that in a second. We have other packages that come from the JupyterLab module. So again, what JupyterHub is doing, it's doing kind of module load Cray Python, then it's doing module load JupyterLab. And so JupyterLab itself loads some more modules as well. And these things get added to the Python path environment variable. So Python is looking in OPT Python 3.8.5.0. It's also looking at Python path, looks in Python path first actually. And then it will also look in, of course, in your current directory, because Python will first of all look for packages in your current directory. And then it will also look for things that you install in .local lib Python 3.8 site packages. And those are things that you will install with pip. So to get an idea of what's already there, you can do pip list. And that will tell you a bunch of different things that are available by default in this Python 3 kernel. And you can see a whole lot of things that are related to JupyterLab. So for example, Py0MQ, the message library, message passing library that Jupyter uses. You can see other things that might be more numerical libraries like NumPy. There's a version of NumPy 1.18.2, likewise Pandas 1.1.0, and so there's a bunch of things that you can see there. If you want to know where Python is looking, you can use you can do a for path and sys.path, and then it'll print out the path. So as I say, first of all, look in your current directory, and then this is a bunch of other directories that it's looking for packages. So yeah, I encourage you to look at these things, and then you should have a better idea of where packages are being found. You can echo the Python path likewise, and you can see that this is the path that's being searched first. And even if you're in a virtual environment, then Python will still look at the contents of this $Python path environment variable. So it's important to know that it's looking in all of these different directories. You can see which modules are loaded. So as I say, when you spawn your notebook, it's basically doing a module load of JupyterLab, Python, IPython, Py extensions, and things like that. So you can just do a module list within the notebook. It's the same as if you were to SSH onto Piz Daint and do module load JupyterLab. You'll see there's a variety of different modules. And then we can see how we import things and where they're coming from. So we import here NumPy, and you can see that it's a version of 1.18.2, and you can see that it's coming from our system directory. So this is a NumPy that is provided by Cray. It's built on the Cray scientific libraries, so technically should be performant. But you can, if you need a newer version, say, I think NumPy is around 1.20 at the moment, so perhaps this is too old for your needs, then you might want to install your own version. And so we'll see how you can do that. Likewise, Pandas, you can see that Pandas, on the other hand, is coming from a directory that is based on Py extensions. So as I mentioned, we have a bunch of modules that are currently loaded in this environment, one of them being Py extensions. So here, Pandas 1.1 is coming from Py extensions. Here we have a small snippet of code where we're importing a couple of libraries, NumPy, Pandas, and then Seaborn, which is a statistical package, and Xarray, which is a kind of a labeled data arrays, so like a cross between NumPy and Pandas. And if we run that, you can see that although we've got NumPy, we've got Pandas, we don't have Seaborn, and we don't have Xarray. So the question is, how do we make these packages available in our notebook? And if we remember on the slides, I said there was a variety of different ways to do them. The simplest way is to simply do a pip install. Now, if I type pip install Seaborn directly in a notebook cell, what it will actually call is the magic, the %sign pip, but we have auto magic turned on, so we're just going to do that. And you can see that it outputs a bunch of stuff to the screen. It says defaulting to user installation because normal site packages is not writable. So in the past, if you wanted to use pip and you wanted to install something locally, you needed to do something like -- user at the end, and then it will install it in your local directory. But the behavior of pips changed a little bit these days. So it actually defaults to a user installation. It sees that you can't write in OPT, Python 3.8, blah, blah, blah. So it knows that you want to do a user installation. So it does the user installation automatically, and it says that it's installed it. Okay. Likewise, Xarray, we can do exactly the same thing. And you can see that it installed Xarray. But what you can also see is that it looks for the requirements that these different things need. And so Xarray, for example, needs NumPy. It sees that it's already finds the NumPy, which is in the system-wide site packages directory. So it doesn't install a newer version, just uses that one. So now we have a slightly uncomfortable combination of some modules, some Python modules that are provided in OPT Python 3.8.5, I see on the system, and then some that are sitting in the .local, your own home directory. So the Xarray and the Seaborn are now going to be sitting in .local /lib/Python 3.8/site packages, but other things are being pulled in from different places. And so this will work. You can see now that if I restart my kernel, and I run this cell, whereas before it was failing because it couldn't find Xarray and it couldn't find Seaborn. Now you can see that it's running perfectly fine. But as I say, it's a mix. So you've got some packages from our installation, and you've got some packages in your own .local lib Python 3.8. Okay. So at the moment it's working, but imagine that, say, we upgrade some of our packages to things that are not compatible with what you've just installed, then you could run into difficulties. And so for that reason, we encourage you, instead of doing this simple way, if you want to have a little bit more security that you're going to have a long-term supported way of working, we recommend to create virtual environments and then install kernels. Creating virtual environments. So now I'm going to share my terminal, and I'm going to show you how you can install, create a virtual environment and install a kernel. Okay, so I'm going to stop sharing this one. I will share terminal. Hopefully you can see that. Can you see that, Harman? And
yeah, I can see it.
Yeah, okay. So what we'll do is we'll SSH into Daint. Is the text size okay?
For me, it's perfect.
Okay, great. So pretty much everything's written in the notebook anyway, so it's not so crucial. So what we do is we load the module CrayPython. As I mentioned, everything is built on top of CrayPython. So if we want something to be compatible, then it's useful to do that. Then we do a module load of Daint GPU, and then we do a module load of an additional module which we call JupyterUtils. And this JupyterUtils is going to make available a special little wrapper that will create the kernel for you. Now, we create a virtual environment, so that's Python -m venv, and then you can choose whether to include the system site packages or not. So if I go tutorial, I'll call my virtual environment tutorial-sp. And here I'm choosing to include the system site packages. And what that will do is that will include the NumPy that comes from the Cray system. If I didn't include system site packages, it would not include that. Okay, so it's up to you. You can choose what you can do. We can have a look at the difference. So we create our virtual environment. And then we source it. Bin activate. And then what we can do is we can pip install various things that we need. So we go pip install Xarray. And you can see that some of the requirements are already found because we said we want to use system site packages. So you can see that it finds NumPy already in OPT Python 3.8.5. Where the other thing we wanted was Seaborn, so we install that. And then the key additional thing that you must do when we create our kernel is to install the IPy kernel. So we go pip install IPy kernel. And so that installs a bunch of things related to the kernel, necessarily like Tornado web server, Jupyter Core, Jupyter client, whatnot. And then the last step is to actually create the kernel. So we do kernel create, and then we call it a name. It doesn't have to be the same name as your virtual environment, but it kind of makes sense too, just so that you know what's in there. And we go kernel create, and you can see that it says created successfully and uses Robinson.local share Jupyter kernels tutorial-sp. Okay, and we can deactivate this if we want to. Now, if I share back on major browser window, Firefox. Now we should be able to see that our kernel is now available for us. So we can select it from here. We can switch kernel over to this one, or we can even create a new notebook and we can use that kernel that we've just installed. Tutorial SP. There we go. And so you can see tutorial SP is up here, and it'll be able to connect. And now it says kernel idle, and we can use this. And our kernel is working fine. Just add. But as we mentioned, this is still pulling some system site packages like NumPy. It's probably the case that you want to have a more clean environment so that everything you can control. But what we'll do is we'll show you how to do that one, which is very similar. I will share back in our terminal. And what we'll do again here is we will create another virtual environment. This time we won't use the system site packages. So we'll just go like something like that. And we will source it. And then we will do more or less what we did last time. install Xarray. And here, this time you can see that it's going to install NumPy for us because we haven't asked for the system site-wide packages. It's going to install NumPy 1.2 because it needs that as a dependency for Xarray. And so we can have some more control. Basically, everything is being collected. SciPy likewise. So previously SciPy was coming from Piz Daint directly, but this time we're getting it from a requirements there. You could also, of course, use a requirements file, and that's what people would normally do. So you would do pip install -r and then requirements.txt, and you would probably have explicitly versioned Python modules. So you'd say, I know I want to use NumPy 1.2.0, 1.20.1 or something, then I would put NumPy equals blah, blah. What we'll do, remember, you need to install the IPy kernel. And in fact, if you try to do kernel create without IPy kernel, then it will give you a friendly reminder that you haven't installed it. We'll run kernel create, and then we'll call this one, we'll just call this kernel tutorial. We'll call the other one tutorial site packages. Okay, so again, it says it's created it successfully, and then we may as well deactivate, although it's not really necessary. And then we'll switch back over to the browser window. And what we can do is we can switch kernel, and hopefully the kernel that we just created will become available. It's not available quite yet. Here it is. So we'll turn on the kernel we've just created. It's called tutorial. Allow it to connect. And then you'll see it's now idle, so it's ready. And if we see now, for example, we do import NumPy and do version, we should see that we have got indeed the one that we just installed, not the old 1.18, which is provided by the system. And likewise, you can see that where it's coming from this virtual environment that we just created called tutorial. All right. And then the beauty now is that you can actually install with pip something else. So now if I do pip install some other package, that will install it into this same directory. So it'll be like you're in your virtual environment. Okay, so this is pretty handy. So next option for installing packages. So let's switch back to our Python kernel. You can use some of the environment modules that we provide. So here, when I say environment modules, I'm talking about things that you do get when you do module load. So you can place these module loads in that .jupyterhub.env file, and that is going to be sourced right before JupyterLab launches. So let's bring up a terminal and open my JupyterHub.env file. You can see that I already have one module in there that I'm going to add something like PyTorch. So PyTorch is provided by CSS using this easy build framework. There's a bunch of modules that you can see with module avail. You can also install modules yourself using Easy Build. If you want to, you can check out the CSCS user portal for information on how to do that. I'll save that file. And now, as I mentioned, you need to now restart Jupyter in order for this to be resourced. So what I'm going to do is I'm going to Hub Control Panel and then stop my server. And basically, as I say, that kind of does a S cancel in the background. And then I'm going to start again. And I might need to just refresh as this cleans some stuff up. And then what we'll do again is we'll just click launch. This time I didn't use the tutorial reservation, but it still should come up hopefully quickly. Okay. So I think I have a notebook which uses PyTorch. As I mentioned, you can put module load PyTorch, which we've done. And then, so we should hopefully be able to import Torch. So let's have a look, see if it works. Cross our fingers. And yeah, it does. So without that module load command, if you just tried that in a notebook yourself, you would see that it will say that it can't find PyTorch. And then we can run our notebook, which does some basic fit of a polynomial or something like that. But this is a good way that we can demonstrate the GPU dashboards. So this third icon from the top, system dashboards it's called, and you can get some information about how the GPU is being used and also the CPU. So we can bring up various panes like GPU utilization, GPU memory, everything, and then you can move these around your screen as you like. And what we can do is we can run this notebook. And so this one's, at the moment, we're using the CPU to do this fitting. So we should see probably nothing in the GPU utilization, but we will see something in the machine resources, which is CPU utilization. Let me put that one over here, for example. We run this. Yeah, it's a little hard to see, but you can see some activity there. You can do that in your own time. If we switch then to using the GPU device and we rerun it, we should hopefully see these things light up with some activity. Yeah, so you can see some GPU utilization, memory, and the notebook's running. So this gives us a kind of a immediate confirmation that the GPU is being used by using these beautiful GPU panels. Here you can see the timeline, and again we can run the code, and you can see some activity. Okay. So we've looked at installing with pip, we've looked at creating virtual environments and turning them into kernels. We've had a look at module load. in your .JupyterHub env. And then there's another option 4, which is Conda. So probably a lot of you are used to using Conda. It's quite nice. And the good news is that you can use your Conda environments also with our JupyterHub. And again, what we're going to do here is we will switch to a terminal, and you can see how you can install mini Conda, which we would definitely recommend above more bloaty things like Anaconda. Mini Conda is a little bit smaller, it's a bit more manageable, and then you can build things on top of that. And we can see if we can get that to work in Jupyter as well. So again, I will switch my screen share to terminal. And we'll start with a fresh login. And the first thing to do here, we don't actually have a centrally installed Conda. So what you can do is you can install one yourself. So to do that, you can grab a version that you want. In this example, we're grabbing Miniconda, which is based on Python 3.9. So you imagine that you want to use a newer version of Python than what we provide, which is 3.8. So that sounds like a good idea. We'll grab it, and then we will run the installation. And I think first of all, we need to read the license. So we'll just accept the terms of the license. I'm going to type yes. And then it will ask you where you would like to install it. And by default, it will try to install it in users and then your username, Miniconda 3, but it's probably the case that you may not have enough space in your home. So in that case, it's best to install somewhere else. And I would recommend to install, perhaps you have a project that is sitting in /project, and then your project name, for me it's CS Staff Robinson, and then I'll call it Conda 3. So you're all Piz Daint users, so you'll have projects, and maybe you can build something like that. So then it will unpack. And it will say that it's going to install this bunch of packages. So these are basically what's required by Miniconda. If you're using the full Anaconda, then it would install a bunch more stuff. But this is kind of like a minimalist distribution of Conda. And then it will say, do you want to initialize it? Yes, and I'll say no at this stage. Otherwise, it will put stuff in my .pro-rc or .profile. And just reading instructions, it says you need to run this line to activate, where your shell name, I'm using bash. Most of you are probably using bash, but you might be using something else. So we type that. And then you can see that with this, that I'm in my base Conda environment. So from here, typically you would recreate other Conda environments, but I'm going to do everything just in base for illustrative purposes. And we will kind of do similar stuff to what we did before when we installed our kernel. Remember, we needed to load the Jupyter utils. So to have Jupyter utils available, we should do module load Daint GPU or module load Daint CPU. This basically just makes the software packages that we provide available to you. So we go module load Daint GPU, we do module load Jupyter utils. So note that we're not having to do anything like module load create Python, because we're not using that Python, we're using the Python that we've installed with Conda. And remember that we need ipykernel. So we're going to do conda install ipykernel. And so that will collect the ipykernel and all of the dependencies. Conda has quite a complicated package manager, which is able to determine all the dependencies. We'll proceed, and it will download and extract a bunch of things, including IPython, of course, because we're going to need that and all of the Jupyter stuff. And it will install everything. And then we can use that kernel create, and we can call it something like conda example. And again, it says kernel successfully created. If we now go back to our main screen, in a few seconds, the kernel should automatically be available for us. So it's not there yet. We should just wait, have some patience. And now it's available, just like that. So we connect to Conda example kernel. And you can see kernel idle, so it's most likely working. I'll double check that it's working. Yep, and remember that we installed the Python 3.9.1. So this verify that this is the one that it's using. And then of course you can install with Conda, install any other packages that you need. And as I say, you probably will be wanting to use other environments in Conda as well. So that's the fourth option that you have to get the Python packages that you need. And as I mentioned, we're considering option 5, which would be a containerized JupyterLab, which will enable you not only to install kernels of your own liking, but also to install JupyterLab extensions of your liking, which is not so easy to do at the moment. So if we continue on a little bit to the next section, which is parallel computing. So if you want to use MPI for Pi or other parallel computing, you can use something called IPython parallel, which is more or less similar to IPython, but just consider it like having lots of IPython kernels all running at the same time. And then you have a scheduler which is able to push work onto the different kernels. You have, for IPy parallel, you require what's known as the controller and then one or more engines. And basically the controller is pushing work to different engines. So usually you have multiple engines. And there's a variety of ways that you can start up the controller and the engines. You can use them at the command line by issuing this command IP controller, or you can use IP cluster command, which basically starts the controller and the engines at the same time. Or you can use a custom magic developed at CSCS and then do an import of IPC magic to make it available. So quickly, we'll go through a couple of the different options. The first one we'll look at is starting the controller and the engines manually, because this is probably the most transparent way to see what's happening. What we can do is we can open up a terminal, drag that to one side, make us a bit more space. And basically all we need to do is to type IP controller start, and then we start it in the background so that we can run some more commands. You can see a bunch of stuff's written to the terminal saying that the IP controller has successfully started. You can use that. You can check that it's running. Yep, it's running. And basically what this is doing is this controller is now going to listen for engines to start. And then if you start some engines that you're going to run the code on, then the controller will be able to manage them. So the next thing we need to do is to start a certain number of engines, and you can do that with IP engine. And you can either just type IP engine and then ampersand as many times as you like, or you can start a bunch of them at once using srun-n and the number. And then if you want to also use MPI with it, you need to pass this --MPI. So what we'll do there, we'll try it out. And you can see again, a bunch of stuff is written to the screen, including things like it checks that it can import MPI. So from MPI for pi, import MPI. And each of these processes is getting their MPI set up. So similar to if you've used MPI with Fortran code or C code, you have ranks 0, 1, 2, 3, and each of these engines is effectively getting one of those ranks. The controller sees that these engines suddenly start up. So the controller, as I say, that's listening for these engines, and it registers them. And so now basically the controller knows we have 4 IP parallel engines, and then you can start to do some work on them. You can import IP parallel and then start the client. And as I say, it's not a this is not a tutorial on IP parallel. You can go to their website and start to use it. But suffices to say that the IDs are registered in the client, and so you can see that there's a 0, 1, 2, 3, and then you can do different stuff using IP parallel. To use IP parallel, there exists these parallel magics. So they're percentage sign px and percentage px. For people that know Jupyter, these are magic commands that are special IPython things that you can't do in normal Python, but you can do in Jupyter Notebook. And so the ones with 2 percentage sign are cell magics. So basically everything in that cell is run by IP parallel. So here, for example, we are saying that on our engines 0, 1, 2, and 3, we import a couple of things, OS and socket, and we print the process ID and we print the host name. So we could just do that on one of the targets, and you can see the process ID 1780 and the node ID that we're running on. We can run on all of them by default. It's important to know that the scoping is in IP parallel things that are issued by IP parallel are not in the default kernel. So here we set A to equal to 1. So on all of the IP parallel engines, A is equal to 1. But on the local kernel, A is not defined. So here we would need to define also on the local. Okay. We started our engines with MPI. So if you know how to use MPI for pi, you can use this directly now in our notebook, which is pretty cool. So here we do import MPI for pi, we import numpy, and then we set up our communicator, the ranks and the com size. We make a matrix of zeros with size by size. So in our case, we have 4 MPI processes, so it'll be a 4 by 4. And then if rank is equal to 0, we basically just make a small random array and we'll print it. And then on all of the engines, we will call this MPI collective scatter from the root process, scattering 1 row to each process. And then each process will print its row. So let's just run it, see what happens. First of all, as I say, the output, the original array A from our 0 rank, and then we see process 0 received, and then it received this row. Likewise, process 1 received this row, second row, and process 3 received. And so you can do everything that you like doing with the MPI directly in this notebook. We have the auto PX magic as well. So instead of having to type PX every cell, you can turn on automatically. So at the moment, if I were to print this, remember this is not running on IPyParallel, it's running the local kernel, so it says rank is not defined. However, if I turn on auto PX and then run this again, then it will consider this like a PX cell, so it'll run it, and you can see that it works. What I'll do is I will shut down my IP controller and IP engines. So kill all IP engine. You can see that they're all died, and we'll there's a lot of stuff which is printed to the screen because the controller suddenly panics that it can't find any engines, and after some time it will realize that they've been killed, and so it will stop. Now it's stopped. And as I mentioned, that we have this fancy way of starting your IP cluster using directly from the notebook without having to use the terminal. So I'm going to kill the terminal, and I'm going to open up the next notebook, which gives a little bit of information about this magic command. It's pretty simple. There's just one command. It's %IP cluster. And then you can pass it a number of processes and say whether or not you want to use MPI. All right. So let's try it. There's a help with -- help. Reminds you to start, stop, and then a version. So we're using 1.0.0. And then we simply do IP cluster start and then the number of engines that we want. And it will say that it's setting it up for us. And then it's ready. And again, you can see that once you start the client, you can see the IDs are there, 0 through 11, exactly as what we would have expected. And again, we just print the host name, and because we're running just on one single node, you obviously all have the same NID ID, and you can do the same stuff that you would do just that we saw before. Setting variables, interpreting. And once you're ready to stop the cluster, you can just stop it with IP cluster and stop. And so that's kind of doing all that cleanup that we previously were doing on the terminal by starting the cluster. by hand, controller, and then engines. This is a much faster and simpler way to do it. We can do MPI, of course, and you can do that the same way that we would have done it before with -- MPI. It says that it's setting it up. And it's ready. So again, now we can, from MPI for Pi, import MPI. And you can see that you can print hello world or do some basic MPI stuff that you want to do. Now, again, you can see that everything is running on one node, but there's nothing to stop us from having multiple nodes. So what I'm going to do is to give a quick demonstration of this. Shut down my server. And then I'm going to start again, but this time I'm going to ask for 2 nodes. Okay. And so we're going to launch JupyterLab again. Jobs running. So she'll start pretty soon, and then we're back in. What we're going to do this time is we're going to start our cluster, and again we're going to ask for 12 nodes. For 12 MPI ranks. And you can see that it says that it's setting up the cluster, says that it's ready. And now you will see that half of the ranks have started on the first node of our allocation, and half of them have started on the second node. So here you're able to do distributed computing in JupyterHub within a few seconds. So I would recommend you try out this IP cluster magic, because it's a lot easier than trying to start the controller and engines by hand. Of course, you can still do everything by hand. Everything's flexible. And if you want some additional functionality that's provided by command line, then yes, you are absolutely free to use command line as well. Okay, and the last thing that I wanted to quickly say before our break, we're running a little bit behind, so we'll go up a little bit faster, is Dask. And this is just to demonstrate to you that we have the Dask dashboard available. Dask is kind of a cool thing. We have a course on high performance computing and Python, which we run each year, and also there'll be one later on this year. And we will discuss how to use Dask. So this is not a tutorial on Dask, but this is just to show you can use the Dask dashboard. And this is how we do it. So Dask you can use for all sorts of different things. You can use it for, say you have a NumPy array that doesn't fit in memory, you can use Dask and it will manage the memory for you. So it'll move elements in and out of memory. And so you'll be able to do some large array operations that you wouldn't normally be able to do because you didn't have enough memory. Likewise, distributed Dask, if you have multiple nodes and your array can fit in the memory of all of the nodes, then Dask distributed will be able to fill those that distributed memory up for you, so you can run in-memory arrays or pandas or whatever you want to do. But it's also kind of a generic task scheduling. So there's all sorts of stuff you can do with Dask. The Dask dashboard is available here on the left. And it's just to create a Dask distributed cluster. It's as simple as clicking on New. And then you can see that this local cluster has been started. And it sees that there's 24 virtual cores on this system. And this is a 12-core Haswell with 2 hyperthreads per core, so 24 core, and there's amount of memory, and it starts 6 workers, each with 4 threads. And you can adjust these by clicking on these buttons. All you need to do here now is to drag this across, and it will basically create a cell for you that will start your task and connect to the client. You can see that these buttons, yellow buttons, have lit up, and there's various things that task provides, like progress and task stream, and so you can move around to your heart's content. It will show you the workers, it will show you a task stream, those types of things. So we just run this and then make a little bit more real estate. We can do something like make a task array. And here, like task array is basically like a NumPy array. And so it's very similar syntax to NumPy. Here it's DA instead of NP. We create 2 small arrays, an X and a Y, and we chunk them. And that basically is the way for that task can move data around. It's like units that it's working on at a given time. And then by running compute, you can see that this, what are we doing? We're doing an arcsine plus a arccos, and then we're summing everything. So again, if we run that again, you can see that this is the progress of the tasks that need to be done. It's divided everything into these chunk sizes, and here are all of the different processes that are running. We should have a total of 24 processes along here, and then it's doing things like sums, and red is communication, and purple is random sum, doing the random generation of the number. So you can see all of the tasks that are happening in this live dashboard. So yeah, I encourage you to try out Dask. There's loads of good material on their website, and you can play around. It's as simple as clicking on this button and starting. If you want to do, we'll have a break in a few minutes. This is the last thing for now. If you want to use Dask on multiple nodes, you can use a thing called Dask Job Queue. And basically what this does is it will start a bunch of Slurm jobs, and then it will be able to connect, the Dask controller will connect to those workers. It works in a kind of similar way that IPyParallel worked. Remember, with IPyParallel, you had a controller and it talked to various engines. With Dask, you have the Dask controller and it talks to various engines that it calls workers. So this will basically create a bunch of workers. You set up your Slurm cluster for what each individual one will look like. So you need to put a few things like number of cores, amount of memory, the project that you're using, the wall time that you want, and then a few extra Slurm parameters. So if you're all using Slurm on CSS, so you know that you need to put the type of node that you want. And here you can put reservation equals interact GPU, and that will ensure that your jobs run very quickly. So let's just try it out. Clear these dashboards. Actually, what I'll do is I'll stop this one first, and then we'll give it a go. What I might do is I'll open up terminal and we can see what's happening on the machine. Whoops. So at the moment, if I look at SQ, you can see that I have my one job running, which is the current notebook. What I've done here is I've set up a Dask cluster using Slurm cluster functionality, because as we say, we use Slurm. And then what that's going to do is when I call cluster.scale, it's going to launch jobs. What is it going to launch? You can look at that through cluster.job script by printing that. And basically it's collected from these options that I have passed above. You can see this is effectively the Slurm script that it's going to launch. So this is very useful for you if you need to debug and you want to know what it's actually submitting. You can look at that. And then when I actually call cluster.scale, what it will do is it will launch some jobs. And so if we go over to our, terminal and we look at my jobs, you can see that it started some jobs, okay? And at the moment they're pending and it will start 4 of them because I asked for 4 task workers. Now you can see it's in configuring stage. And so soon it will be running. Now it's in prologue. And it will soon be running. Now they're running. And our controller knows now that they're running because you can see that it automatically sees that there's 4 workers. And so if these workers, if we shut them down, then Dask will know that we've shut them down and it will be able to manage things itself. So you can scale these, we can add more, we can reduce them, we can add more workers, and we can do these sorts of things. So we bumped it up to 6 workers, and you can see that 2 more have started or are in the process of starting. And so you can see now that there's 1 has started and another one's in prologue, and you'll be able to see immediately that Dask knows that there's now 6 workers available. And so this is a very cool way to be able to grab more resources. If you're working in one notebook and suddenly you need a lot of computational resource, then you can just use this Dask job queue and just grab some more nodes and do some work. And then you can just turn them off again. So then I can go cluster.scale back to 0, and you'll see that they're now in completing stage. And so now they've finished.